Welcome to our lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the Laboratory for Quantum Materials and Devices. We would also like to give special thanks to the NordTech Hub and the Microelectronics Commons for their support in making this lecture series possible. This lecture series is the product of the combined efforts of the NYU Nanolab PhD students Moed Jamalzadeh, Miguel Monzo Perez, and Ilya Shiravand, under the guidance and support of Professor Davud Shargerdi. As a team, we set out on this educational mission to present superconducting resonators in a clear and accessible way to a broader audience while maintaining scientific and academic rigor. Our goal is to address both general and specific questions that arise when learning to design, fabricate, measure, and analyze superconducting resonators. The motivation for this lecture series comes from the central role that superconducting microwave resonators, particularly those in the coplanar waveguide geometry, play in cutting-edge technologies. In the late 1990s and early 2000s, a key breakthrough took place: the experimental demonstration that a single microwave photon, stored in a high-quality superconducting resonator, can coherently couple to a superconducting artificial atom. This achievement launched a new era of quantum optics experiments and gave rise to the architecture now known as circuit quantum electrodynamics, or circuit QED. Circuit QED had helped advance our fundamental understanding of light-matter interaction. Almost simultaneously, researchers applied circuit QED to quantum information processing. In this context, superconducting resonators act as high-quality microwave cavities that couple to artificial atoms, commonly called qubits. The resonators enable qubit control and readout, and even mediate interactions between qubits by serving as a quantum bus. In essence, superconducting resonators function as very special kinds of wires for qubits. Understanding their behavior is therefore essential for building scalable superconducting quantum processors. Another powerful application of superconducting resonators lies in kinetic inductance detectors, widely used in astronomy, cosmology, and particle physics. These detectors exploit the fact that the kinetic inductance of a superconductor changes in response to incoming radiation, such as photons. By tracking variations in resonator parameters that are sensitive to kinetic inductance, it becomes possible to detect radiation with extremely high sensitivity. This makes kinetic inductance detectors uniquely suited to meet the growing demand for lower noise, lower loss, and higher multiplexing, where many resonators can be read out simultaneously. This lecture series is designed to provide you with an in-depth understanding of superconducting coplanar waveguide resonators, how they operate, what limits their performance, and how engineering decisions influence both their strengths and constraints. Therefore, by the end of the series, participants should be equipped to understand the theory of superconducting coplanar waveguide resonators, design and simulate CPW resonators for given requirements, and understand measurement practice, microwave measurement chains, relevant metrics, relevant equipment, and general good practices. This lecture series is organized into 3 parts. The first part covers the foundational concepts. The second part provides detailed explanations of resonator design and microwave simulations. Finally, the third part focuses on resonator measurements and microwave data analysis. We at the NYU Nanolab sincerely hope that you find this lecture series valuable for your professional and academic growth. Thanks for watching, and see you in the first session.